Hello and welcome everyone. So we'll again resume machine learning in this session. If you remember from previous session, so we introduced a lot of concepts of machine learning, what supervised machine learning is, and then what unsupervised learning is, what is reinforcement learning, what is semi-supervised learning, and a lot of other more concepts. What is a task, what is an experience, and what are different metrics. So now today's session's goal will be to introduce a problem and to tell you all the terminology, or most of the terminology that we usually use in the machine learning. Okay, so we'll just do it with a synthetic example. We'll do something with data, and we'll maybe generate a synthetic data, and then we'll try to introduce those terminologies. It'll be easier that way. Okay, so that's my goal. Now we have data. Let's suppose we have some data. So data, what it contains? It contains information. Okay, it has an information in it. I won't go to mathematical data right away. So I first want you to have an intuitive understanding. So in the data we have the information, we have all the assumptions that we have, and we assume that this data comes from a certain distribution, and from that distribution we want to learn it by machine learning, and that's an unknown distribution. And now that information, what it does actually, it actually contains surprise. Okay, I'll explain you what it means. So let's suppose you observed some data. If you are not surprised, that means it didn't have much information. So what I mean by that, if you just took a data point, if it was a data point and you already knew a lot of things about it, you expected it to be this way, okay, then it contains very less information. Okay, that means if the surprise is very less, the information is also very less. If now you are more surprised, okay, let's suppose you did not know something. When you saw the data point, you came to know about that thing. So what happened that now that thing contains more surprise, that means it contains more information. And we'll see all this in information theory. We'll see what entropy is and everything. I'm just giving you the intuitive explanation. So now we have data and you are seeing a data point. If you came to know about a lot of things by seeing the data point, that means the data point contains a lot of information. Okay, so degree of knowing, degree of how much you came to know, degree of the enlightenment is the degree of the information that data point contains. Okay, that's what we want to reveal. So this data basically comes from a distribution. I'm again using loosely those terms because we have not yet covered the probability part, what actually we mean by distribution mathematically. So we have a distribution from which we assume this data comes, and this distribution is unknown to us. Okay, this is unknown. Okay, that's the whole game of machine learning. If the distribution is known, then why are you doing machine learning? So now what I said is this data contains information. It contains something that we are interested in. And what is information? It is the amount of surprise, how much surprised you are. If you do not know something, you just pick a data point and you say, oh, I got to know this. It somehow surprised you. The amount of surprise there was in data point, that's how much information it captures. If you are so much enlightened by that, okay, that's how much information we'll have. Now we can just have any type of data. You can have data about image, you can have data about audio, you can have data in terms of text and all this data. And many of the terminologies that we use in machine learning, you will see them almost coming in 99% of examples. So here we'll use a synthetic data example, and the reference is Bishop's book on deep learning. It's a recent book, I think published in November 2024, and I will probably use the example from there. So now we'll see that. Oh, not moving at all. Give me a second. Now let's assume a problem. So what we have is, let's suppose we'll have a variable x. Okay, if you don't understand, just raise your hand and then ask me the questions. I'll be happy to clear the doubts if you have any. So now what we'll have is, so let's consider an input variable which we denote by x. So this is our input variable. So we'll keep a problem very simple so that you understand the concepts that I'll introduce, and then we'll take the algorithms of machine learning and deep learning. So you have this input variable. Let's denote this by x. Okay, then we have a target variable. The target, let's call that t. Okay, so this input and this target. So now from this you can know this is a supervised setting. Supervised setting or supervised learning. Because along with this data point, along with the input, you're also given the target. Okay, and this x and t, let's consider that both are continuous. They take continuous values. They take continuous values. What I mean by continuous, as they can take a value from real number. Okay, and this x comma t, it belongs to these real numbers. Okay, so that means it can take a value of 1.5, x can be 1.5. Let's suppose t can be 4.6, something like this. It does not take discrete value. This is the setting, and now the thing is that we have a training set which contains n observations. So we have a data set. I can call it data set or a training set. Data set which contains, let's suppose, capital N examples. So what is that then? Because we have this x is a variable, so here we will have x1, x2, x3 till, let's suppose, xn. So this over here, so if I call this capital X, let's say, so this over here is my data set. Okay, this is my data set, and these are my individual observations or individual features that I have. Okay, and this is my one data point, second data point, third data point, and fourth data, because I have only one feature over here. Okay, so this is the input variable. Input variables, and now corresponding to that, I'll have targets. Okay, I'll have targets like t. This will be t1, t2, t3 till tn. This is my target. Okay, now the goal of this problem will be, if you somehow can predict, if you have these seen values, okay, then you have some unseen values also. So this, let's suppose, is the whole data set. If I just split the data set from x1 till, let's suppose, xn minus 100, okay, and from xn minus 100 till xn, okay, and this I'll put it closed. I think we know about what intervals are. So let's suppose this is my seen data set which I can see, and this is my unseen. Okay, so I have seen data set on which I want to do something, I want to learn. So because this I assume contains information, and this I assume that comes from a probability distribution. Okay, and now I'll feed this into a machine learning, deep learning, whatever algorithm. Now my goal will be to predict these t's, because these seen data will be, it will have its let's suppose these corresponding targets. X1 will be accompanied by t1, x2 by t2. Okay, let's suppose for these things they do not exist for us. Okay, let's suppose from t n minus 100 to tn, they don't exist for us. Now the goal of the problem is that you have to predict this t for this unseen examples. That's the goal that we have. Okay, so what's the goal? Predict target for unseen data. Unseen data. This is our goal. Now what we have is, we'll first generate this data, because now in order to show you how the data is actually captured in the real world, so what I'll do is, because I won't take a real data set directly. Okay, so now let's suppose I know the distribution it comes from. Let me be, because God knows. Okay, for the sake of simplicity, let me be the God for this example. Okay, I will know that what distribution this data comes from. So I'll generate the data. So we'll have a process of generation of data. So we'll generate this data. Okay, because when we generate, we'll call it synthetic data. Okay, so I'll generate this data. So how can I generate this data? Is I can use a lot of functions. I can use a lot of functions by which I can generate data. So in order to actually capture the real world sense of data, so what I'll do is, I'll use a simplistic function. Let's use a sine function. I'll use a sine function, sine of 2 pi xn. Okay, so this function I'll use, and based on this I'll generate the data. Okay, now you can see that this is a deterministic process. Okay, if I just give the value of x to it, it will give me a target. Okay, and x, I can form the pairs of x and t. Okay, and this is the function by which I'll just plug in the value of x, and it will give me the value of the target. So this is my f of x. So f of x is equal sine of 2 pi x. So this is how I'll generate data. But if you see, real world data does not only have pattern, it also has some noise associated with it. So I'll add noise with it also. I'll add noise. Okay, and in particular I'll here add Gaussian noise. So this is how I'll generate my data set. So what I say is, so real world data, it has some pattern. That's what we want to learn, because machine learning somehow captures the pattern. It captures the probability distribution, and that probability distribution will be somehow well defined. It won't be just any sort of thing. Okay, otherwise it will be very hard to learn from it. So what we assume is that there is a function, probably a very complicated one in real world data set, but here we are making a simplistic assumption that, let's suppose I am the God for this example. I know the distribution it comes from. I know the function that is generating this data. Okay, so let's suppose this is the function. So in actual deep learning there will be a lot complicated functions, and we won't have closed form equations for the data. So here let's assume that this is the function which is generating the data, and in order to capture the real world sense of data, so what we should do is, we should add some noise, because there is a pattern and there is a noise. Okay, that's what makes real world data difficult. And where this noise comes from? It comes from intrinsic randomness. Okay, there's uncertainty involved everywhere. Even if there is a pattern, if there is a clear pattern, but still you can see that somehow it deviates from that pattern. Why? Because there is an intrinsic randomness associated with it, and other things can be, there can be unobservable source of variability. Okay, some environmental factors, some other things which introduce this noise. Okay, in order to mimic what happens in the world, how do we assume that data is? So there is a pattern. Okay, now I said two things about the real world. So when you have data, so there is actually a pattern in that data, but that pattern is not quite visible directly. Why? Because it is somehow randomized by noise. There is noise associated with those samples. Because if you just have pure pattern data, that's not real world data then. Okay, because real world data has some noisy things in addition to the pattern. Why? Because I said, let's suppose because of radioactivity decay, if there is some intrinsic randomness, if there are some environmental factors, or something else. So this pattern is there and this noise is there, and our goal is this. Our goal is to capture this pattern. This is our goal. Okay. Now what we want basically is, we basically want to learn this function. We want to learn this function from the data. If this data is given to us, and we should learn the function. That's our goal now. Okay. Now let's go to the code window and I'll show you that. Okay, let me just go to the code window. Give me a second. So now you understood that the process of generation. So what I said is, there is a pattern in data, and in the real world data there is some noise associated with it. So now what we'll do is, I will be the creator of this data for time being, because I know the pattern, where the pattern comes from, and I also know where the noise comes from. The goal will be to learn that pattern, not the noise. Okay, so what I'll do is, I'll import NumPy and Matplotlib, because I'll also plot it. So going here, just hold on for a second once I do it, and then you can ask me questions. So this, I have imported NumPy and Matplotlib, and what I'll do is, I'll generate a function. So in that, I'll also generate a Gaussian noise. So I'll write a function. So here you can see definition, generate a centric function, and this is n number of samples I want to generate, and noise, standard deviation, because in here, if you know, in Gaussian distribution, you have this mean and standard deviation. And now I'll also give a random seed for the reproducible purpose, if you want to do it yourself also. What I'll say, if random seed is not none, so then assign this a seed. So what I'll do is, I'll say if random seed is not none, then np.random.seed is this random seed. Okay, so that you can reproduce the results yourself. And then I'll generate uniformly some values which are between this 0 and 1. Okay, because I want to generate values for this sine of 2 pi x. So for this, I need to generate this x values first. Okay, this is what I do. So I am generating x is equal to np.linspace 0, 1, and number of points, this should be n. So what it does is, it will generate uniformly spaced x values in the range of 0 to 1. Okay, after that, what I'll do is, I'll compute the target value, because I know how to compute target values. So the target values will be computed like this. X true, this t value, target value, is np sine of 2 pi of x. Okay, that's what I said. This is my actual value that I want to compute. And then I'll add a noise to it. I'll add a noise. So I'll add that Gaussian noise with the mean 0. Okay, now what I do is, so this is my noise, np.random.normal. Okay, basically normal distribution is also called Gaussian distribution, with the mean of 0 and the deviation of this noise, standard deviation. And what's the size of n. So that's how many points should I create noise. So here, let's suppose if I create n number of points, so this t will also be the size of this will be n, and the noise also will be n. Now what I'll do is, I'll just add this x and noise. Okay, so that I get the final point. Okay, so if you see this, so I want to add the target. So because I have this x value corresponding to this, I'll have to add this t true and the noise, because that is the last value, the target value, and for which I'm adding the noise. So I'll do this. I'll say the final point, the final t is equal to t true and the noise. Okay, so this is my final value. Okay, then I'll return this. I'll return my data. This is the data that I have created. I'm saying return this x and t, that is return the original this x. So these are the input variables, and this is my target, and this target is noisy. There is a pattern, clear pattern, this pattern is here. Okay, and this is my noise that I am adding. And then if I want to plot it, okay, if I want to plot it, I'll again write a plotting function. Okay, so this is my data generation function, data centric generation function. So now I have this plot centric, and I give x value and t, and I'll give a title also. So I'll say, if I want to save it also, I can save it, but by now you should be very much well versed with the code I write in Matplotlib. Should not be very difficult for you people. So now you can see it over here. So I'm plotting the figure, you can see it. So here I'm calling this function. If you see, this is my x and this is my t. So I'll call this function. I'll first initially call this function so as to create generate the centric data, and then I'll call this function so as to plot it. Okay, what I'll do is, so I want to create 10 points. Let's suppose n is equal 10. So I'm saying n is equal 10. Let me just take it here. Okay, if you see this, so n is equal 10 number of data points. This is my noise standard deviation. Okay, and this is my random seed if I want to reproduce the same thing. So x comma t, this is my input variable and this is my target variable. I am saying generate synthetic data. Okay, n is equal to n and noise is this much and this is the random seed, and then I am saying plot this also. If I plot it, so you can see it over here. So this is my plot. So this is my data point. So just let's suppose if I increase number of points, if I increase it to 100, then you should see a sinusoidal pattern. Okay, and with the noisy part, it's not clearly sinusoidal. Okay, there are some noisy also. I wrote the noisy observation over here, but I just wanted to be plotted with the 10 points. Okay, so I hope this is clear. To any questions on this? Any questions? Okay, now coming back to this. So if you see that this is how we generate data. So what I said is there is a pattern. So what is that pattern? So that pattern is sine of 2 pi x, sine of 2 pi x. So this is the generating function, and then there is a noise. Okay, and this noise is normally distributed with some zero mean and some standard deviation of 0.1. Okay, so and we discussed at length what I mean by noise. Basically anything that is unwanted for me, and I want I assume that is a noise because that disturbs this pattern that I want to learn. Okay, and this pattern is actually important to me. This is how I generate this data. Now what we'll do is we have to predict these things. The objective is to predict if I am, let's suppose this is these are my values. If I know the values till here, so okay, I have these points. These are the points which I know the target values also. So I have the input values and I have the target values as well. So let's suppose somebody gave me some inputs like this. Somebody will give me input like this. So these are the input that I'll call as test input. Let's suppose these red points or red dots. Okay, so I have to test for these. Now in order to do this, somehow I should find a function which is generating this data. Okay, that I know, but I should learn it somehow by using algorithm. So here I'll skip the algorithmic part. The objective is to use the string data, so to use these blue points, okay, to predict the target variable t for these new variables, okay, for these red variables, the red variables I have here. Okay, the objective again, to reiterate, is to use the training set, these blue points, okay, in order to predict the target value for these values. And here I can see it, I have the target values when I draw these points also. But they'll be just given as points to me. They won't be given on the graph. They'll be just given as they'll be given x values, because when I draw this point, let's suppose this point, so I give x value as well as t value to it. So this is my t value, this is my x value. So but how these points will be given? So these points will be given to me like this. So this is my x value. I'll be just given x value. So I'll be given this point. I'll be given point like this. I'll be given point like this. Okay, I'll be given point like this because I'll be given just one value, that's x value, and from this I'll have to get the target value. So for example, for this the target value will be lying somewhere around here. Okay, somehow I should predict this. So I'll be given, so this over here, if you see this, so this is my test set or the unseen data. Okay, all these blue points over here, these are my training data. Okay, this is the objective. From these blue points I should somehow learn a function, I should capture the pattern, and then these points which are given to me, okay, because they have this only x value, I have to predict t value from there. So okay, once I somehow came up with the function that is generating this these observations, I will easily be able to predict what is the t value for these x values. Now the challenge here is we have this finite data set. Okay, I'll just, so we have the finite points. So if you see, we have the finite data point, finite data set. Okay, so we have to we have this finite data set, and from this we have to generalize. Okay, and it is inherently very difficult because you don't know from the finite is it represent the whole population, because data can be infinite and that infinite thing might represent the population, might represent the actual probability distribution. So what I say, this problem is inherently difficult. And why? Because of this finite data set. Okay, because you have access to finite data. So in the previous discussion also I told you that the more you increase data, the high probability is that you are going close to the actual probability distribution. Okay, so there is a probability distribution, let's call that P. Okay, the more points you sample from it, the closer you go to this. Okay, and how to quantify this? Then the probability theory comes in. Probability theory, because there is an uncertainty. Okay, when you sample the point, there is uncertainty. So then probability gives us the mathematical framework. So this probability It gives a mathematical framework to quantify this uncertainty. We can quantify the uncertainty. So what I said is, the more points you have, it somehow approaches the exact probability distribution. But we have this finite data set. That's why I said it's inherently very difficult. This problem is very difficult to solve, because we have to generalize, not to memorize. Okay. And then once we have this mathematical notion to capture this uncertainty and to quantify this uncertainty, then comes the decision theory. So what the decision theory does, it helps to leverage this probabilistic representation to make an optimal prediction. Okay, based on this, we make prediction. Based on this, we try to quantify this uncertainty, because as I said, this problem is inherently very difficult. In order to get the problem, we should have whole data set, and there will be infinite values of there will be infinite points in the data set. So, but we have this finite data set. From this, we have to come up with this actual probability distribution. What I said is, the more we sample, the closer we get to the probability distribution. So now we cannot get the whole data set, so there is uncertainty involved. So that uncertainty is captured by probability. Okay, the uncertainty is quantified by probability. So now once we quantify that probability, once we quantify this uncertainty by using probability, then we leverage this probabilistic representations to make some optimal predictions. Okay, that is done in decision theory. Okay, so these are the two things where the mathematics chips in again. So probability is used to quantify uncertainty. So in order to we have this probabilistic representations in order to make an optimal prediction based on that. So we use decision theory. Okay. Now that's where this probability and decision theory comes from. So learning probability from the data, it's a core thing to machine learning. Okay, and we'll explore these ideas once we go to these probability, and once maybe we'll also touch a bit of decision theory. Okay, and maybe information theory as well. Okay, so we have this finite data set now. So now the point is, what we'll do is we'll do a simple algorithm that's called as curve fitting. Okay, what we'll do is we'll try to fit a curve. We'll have curve fitting algorithm. Okay, now if you see the data that we had, if I again bring up the code, you can see it over here. So this is my curve fitting. So if you see this, somehow I should fit a curve onto this. Okay, and we have learned a lot about curves. We have learned a lot about lines, linear surfaces, and then we can also have parabola. Let's suppose if I just have this, if I want to draw a line, so I'll say W0 plus W1 x1 is equal to 0, something like this. Okay, so this will be a line. Okay, and if I want, let's suppose now a parabola, a line will be there. If I want a parabola like this, I'll put just square. I'll put square over here. If I can have curve like this. Okay, I can have different sort of curves. And now I have to fit this curve. I have to fit in these curves. So I can take a combination of these curves. This. I can just keep on adding the power. Okay. So what I'll do is, so I'll write an expression of curve fitting. This is what I want. So to fit this curve onto this data, so what I'll do is I'll write the expression of a curve. So I have this y, x, comma w. So this is my curve fitting. This is how I'll fit the curve. So I'll say w0 plus w1 x1, or w1 x, let's say, plus w2 x square, because I have this x value only. There are not multiple features. There's just one feature, plus w2 x cube, and so on. And then I have wm x to the power m, or I can just write in short as summation of this wj xj, j goes from 0 to m. Okay, so this is my curve fitting. So if you see, this is an nth degree polynomial. So here I have mth degree polynomial. Here I have degree m, the highest degree is m. So I have to fit this. So now if I just stop it here, so I'll fit a line. If I just stop it here, I'll fit a parabola. Okay, then I'll fit a cubic polynomial, and I'll keep on increasing powers, and the more powers I give it, the more degree of freedom I'm giving it. Okay, and many of you might know Taylor's expansion and things like that, and we'll see how that relates once we go to the mathematical part. But here I assume that till here you know. Now if I increase one more power, so this is x square. So what I do is, so I am trying to fit a parabola. Okay, then here I am trying to fit a cubic polynomial, and you can see the response calculator and just give these. And now if you see this function, this is a function. Okay, so this function is linear in these in the parameters w. So this is a linear function. So this is linear in terms of coefficients. Okay, and this is what we want to learn. This w1, w0, w, and I want to learn this w. This w0, w1 till, let's suppose, wm. Coming to Arshan's question, this is what I mean by parameters. These are my parameters that I want to learn. Okay, so I have to fit a function. So I have to fit a function on this, the data that I have. So I have to fit a function onto that, and this function is that. So here what I will say is, I have to make a lot of decision choices. The first thing I have to make a decision is, okay, what degree of polynomial can I use? Can I use 3 degree, 4 degree, 5 degree, what degree can I use? And I have to learn these w's, what values should I assign to these w's. So I'll fit this polynomial curve. So what I said is, so if I just take this part, okay, so this is this is my line. So if I take this parabola, line plus parabola plus, let's suppose, something cubic polynomial and some higher order polynomials, so take all the combination of these and you can come up with this poly. You can come up, let's suppose, with sine function. You can approximate the sine function. So sine function looks something like this, let's say. Okay, now if I want to approximate this, so I have to combine this plus, let's suppose, parabola plus third order is something like this, fourth order is something like this. I don't know what orders, how the shapes it, that you can check. So all these the things will be combined in order to get this. Okay, take a combination of this in order to come up with this. And there's the approximation theorem also, which says that you can approximate every function and you can expand this. You can use Taylor's expansion to show that any function can be approximated like this. Okay, now that's my goal. Now my goal is to fit this, basically to fit this is my function, and this will give me a curve. Any questions till here? Any questions? Yes, question. So this is the thing that I want basically to I want to fit the curve, and by the help of this thing I want to do that. So this m basically is the order of polynomial, I'll just write it down. Okay, this is again a Hebb parameter, and we'll see how does it affect. And then these wj's, or this w0, w1, w, and these are coefficients of polynomial. I'll just write it in short, coefficients of the polynomial. Okay, then I have this w vector. Okay, so this w vector is combination of these coefficients. So a vector that's collective represents all of these. So this w is this w0 comma w1 till wm. Okay. And then I have this x, j, x to the power j. So this actually is represents x is to the power of j. So yeah, I think it's pretty much clear. So now if you see there is the input, actually the input, it is non-linear input, but it's linear in terms of coefficient, and we want to find the coefficients. Okay, now let's do that. Let's do this curve fitting. Now let's say what we'll do is, I'll bring up the code window and then I'll show you if I fit the curves. Okay, let's suppose if I randomly do this, if I let's suppose fit only a line, if I fit a line like this. Okay, so you can see that there will be this is not the, and you can clearly see that this line is not actually giving the value that I want. It's mispredict. It's this prediction and there are a lot of mispredictions over here. Okay, so what I can do is, if I just use a parabola. Okay, if I just use a parabola. So if I just use, let's suppose, parabola down like this. Okay, so something you can see that all these points will be missed out then. Okay, somehow I have to use a combination. Now I have a curve fitting thing. Now my question is, how can I see that how good this curve is? Okay, I should quantify how good or bad that this is. Okay, how good or bad this is. Okay, I'll give an example in physical sense so that you understand this. Now I have an example. I have data. So on this data, I am trying to fit in curve. So I have a machine which I call as curve fitter. So curve fitter. So what this has, let's suppose I will use this equation. Now I have this w0, w1, w2 till wm. So let's consider these are my knobs. Okay, I can tweak and adjust them. Okay, and this curve will get adjusted accordingly. Okay, so let's suppose if I have till a power m. So once I adjust these things, so this is my data, or the data that I had. Okay. So the moment I adjust these, so this curve gets adjusted accordingly. So it depends on the values of these knobs. Okay, so if I start with, let's suppose, something like this. So if I change the values, okay, if I tweak the values, it will get a bit smoother. So I'll find the configuration which somehow does it like this. And now this is the data. I have a curve fitter where I just tweak these knobs in order to fit this curve. And now how good is this curve? So okay, how good is this curve? In order to find that, let's suppose I fitted this curve. Somehow I had a curve like this. Oops, I had a curve like this. Okay, now how good or bad this curve is? Good or bad? So what I'll do is, I'll fit this, I'll give this curve onto some other machine. I'll give this curve to, so this curve will be an input to this machine. So this machine will quantify how good or bad, and it will give us a metric. So it will give us a metric, okay, based on which we can decide that this curve is bad and this curve is good. So this is actually called as error function. So this again is a function. This is called as error function. What we are doing is, so this curve fitting, it's a function. So we are trying to give it these things. We are trying to give these parameters that we want to learn, and it's giving us an output a function. Okay, that basically the curve that we want to fit on the data. But how good or bad is that curve? So we again give all these things, we give that curve to this function. Okay, and this is that, and we want to give to this function. So this function is again a machine sort of thing. So it tells you in a metric form, okay, how good or how bad this is. So what is one metric that we can use, and how can we come up with that function? Okay, I'll just use a simple function, that is sum squared. So if you see, so our points were like something like this. I bring the code over here. So let's say, so this is what I have. Let's suppose I use something like this, or maybe let's say something a bit smoother. Okay, so now what I will do is, in order to see how good this curve is, okay, so what I can do is, give me a second again. So I'll see, this is the actual prediction. Okay, for this point, this is the actual prediction. Okay, but my curve predicted this. So now if you can see, there is a disparity. There's a disparity between these two. So this much disparity is there. Okay, and for this much disparity is there, and you can clearly see that it is making some wrong things as well. Okay, maybe for this it's the loss is very less. Okay, the error is very less. So error is how far it was. And now in order to quantify the error, what I can say is, I'll say that I'll say y of x, let's suppose this is nth point comma w. Okay, so this is what was predicted. Okay, and this red line is the prediction. Okay, and then this was the actual thing, this t was the actual thing, this was the nth point. For nth point, this is what my y value predicted, this is my prediction function. Okay, the curve fitting algorithm. And now I have to quantify it, okay, how good or how bad it is. So I am saying this is the prediction and this is my original thing. So I will subtract them. Okay, I'll subtract them. I'll see how far is it from the actual thing, how far is the prediction from actual thing. But it can be negative and positive. In order to make it positive, I'll square this thing. Okay, so once I square this thing, so I'll do it for all the points. I'll do it for all the points. I'll sum up for all the points. I'll say, since this n goes from 1 to, let's suppose we have some n points. Okay, so for all the points, I'll see how much is it deviating. So actual value I wanted this, but it is deviating this. But in order to just negate that thing, because I don't want, because there will be negative positive values, I want just positive error. Okay, and at the end I just will put this 1 by 2. So this 1 by 2 is put for the convenience, because we have to differentiate this. We'll get into mathematical details, and then we'll see this 1 by 2. Once we differentiate it, this cancels out. Okay, and you can, otherwise there is no significance. Why do I put this 1 by 2? Okay, so this will give me an error, this will give me a number. So this thing over here I can call the error function. It's an error function. So what is it again taking value? It is taking this whatever I fit. I have these w's. Okay, so I have a curve fitting algorithm. I set and tweak these knobs, so I get a curve out of these w's. Okay, now take these w's and fit these things into that error. Okay, what I'll give you, so that thing will give you some error for each data point. It will tell you how far is that data point from the actual prediction that we had. This is our prediction, this is the actual thing. Okay, now we have to square. We see how off is that, and this will be a number, so this will quantify. If the number is high, that means this is missing it by a lot. If this number is low, that means we have a good fit. So it will be a range. Let's suppose it can have a value 0. When it will have a value 0, if all these things overlap. Okay, if the predictions, if this thing minus this thing is 0, okay, that means this thing is equal to this thing. When the prediction is equal to the actual value, then we will have error of 0. So we want error as less as possible. Okay, but not on the cost of memorization. Okay, how many of you are understanding this? So we have two things now. We have a curve fitting function. You just have these w values, you adjust these w values, and out of that you get a curve on which you can fit onto this. But now in order to quantify how good this curve is, what you do is you came up with an error function. You said, okay, I have this curve now, okay, let's fix this curve. Okay, based on that I'll make prediction for all the points. I make prediction and I'll see what are the predictions given by the curve that I selected. Okay, and out of these lot of curves, so I'll select the one which has the least error. Okay, so I'll call that w star. So once I am convinced that this E of w is minimal for a particular w, I'll call that optimal w star. Basically this is the optimal w, I'll call that w star. So here I got the least error, okay, that I wanted. So is this clear? Any questions till here? The question is that we want the least error possible. Okay, now the question that Muzaffar asked is that because I made a comment that error should not be on the cost of overfitting. So what I mean by that is, so okay, if you see that the test error is dropping, you can see that the error that we are getting up from the test set, it is very less. But when you when you are seeing that error on the trained data set is dropping and it is very less, but when you test it, actually the error is very high. Okay, that means it has not learned, it has just memorized the data set, it has learned what it has memorized what it saw. So that will be our metric. So we basically want to generalize. Okay, we want to generalize. Okay, so what I want is, I want error as less as possible, but on the cost of generalization, not on the cost of memorization. By that I meant, so when you have train set, so when you are training, you'll continuously see that error is dropping, okay, and then if your error is least now, so you have to again test it. So on the test set, if the error is very high, so that means this has somewhat memorized data. It has not learned the actual distribution. It has memorized all these points, and we'll see that memorization in a short while. So here this will be our metric. So we want the error to be least, but when we also test it on the test data set, there it should somehow give a balanced answer. It should not be giving a lot of error on test data set. You can see that if I make a graph, if you see something like this, on test it's getting, on train it's dropping, and it's almost going near to 0. But on the train it was this was on the train, so on the test it was dropping, and it spiked over here. Okay, and this point over here you can say that okay, I should take a value over here. Okay, but because after this I can see training error is dropping, because it's tweaking all these parameters so that it fits the whole data that I have given it. It fits the data that is trained in the training set, but it is not respecting the test set also. So, but we should respect the test set. That's why we check it for the test loss also. How much is the error on the test set? Is that clear?
Yes, sir. Makes sense.
Got it. So here what you saw is that we are using the error. We said y of this xn nth data point, comma, if you have this w. Okay, and then what you say is, and you subtract it from the actual value, actual target, and this is the predicted target, and this is the actual target, and you square it up and you sum it over all the points, and this n goes from 1 to n, and then you add this 1 by 2. Okay, so this is called as mean squared error. Mean squared error, not exactly mean right now, it's just squared error over. Mean we'll call it when we divide it by 1 by n. Okay, because we are not dividing by 1 by n right away, so we are not taking the average. So right now it's just squared error, we are squaring the error. Okay, then we are adding this, multiplying this 1 by 2 over here. Again, to reiterate, so we have two functions involved. The first function that we have, so when you tweak these knobs, when you have this w1, w2 till let's suppose wm, so you get a value, you get a curve out of that. So once you get the curve, now you have to see how good that curve is. So you feed that to this error function. So this e of w. Okay, this e of w is there. So if you see this function, so we had this y of x n comma w. So this again is a function of w. So this again is a function of w. So this is this function we usually call as cost function. Okay, sorry. So we here over here. So what I can do is, so I don't want to go into the cost function in that, because otherwise it will. Okay, so let's sort of settle on this discussion. So this over here is my curve fitting. So this is my curve fitting. This is cost function. Otherwise I have to teach you some more stuff. So here this is my curve fitting, and this thing is my captioning error function. So there are two functions involved. So one function is that by the help of which I can find the curve, and then how good is that curve, I have to come up with a new function. Okay, I have to feed that thing. Now there are two machines. One machine is telling you okay, this is the curve, and second machine is telling you how good or bad is that curve. And now if you see this, the objective is to minimize this. So that's my objective. The objective is to minimize this error. Okay, so now we have somehow formulated the problem. The problem was, so you have some scene data. You have to find a structure in the scene data. You have to find a pattern in the scene data. So once you learn that structure with that pattern, so you should somehow say something about the unseen data. You should say something about that target value if you are given the input variable. So what I did is I said, okay, I'll use the curve fitting algorithm. I'll fit a curve onto this data. Okay, because it seemed very trivial problem, and I can see that curve fitting is quite a good match for it. Okay, if I fit a curve onto that, so what I did is, so I said, okay, somehow can I formulate this problem like this? So I have a curve fitting algorithm. How good or bad is that? So I am formulating that problem like this. So here you can see this function is also getting used. So this curve fitting function is also getting used. Now how less error, how can I get this less error? So I have to minimize this function somehow. That is the objective now. The objective to find the value of this w. So if I have to find the value of this w, okay, I should for that particular w, because this w can take infinite many values, uncountable infinite values. Now the objective of the problem is to find that w which minimizes this error, and again not on cost of overfitting, on the cost of generalization. So we should try to generalize it. It can be least for training, so we should generalize this. So we should minimize this error and try to generalize. Okay, and that we will have a resulting polynomial after that. Okay, any questions on this? Yes. So now you saw this equation. If you see this equation, If you see what this equation, the first one, this y, x and w. So we wrote it like this: w0 plus w1, let's suppose, x plus w2 x square plus and so on x, this wn or wm, we wrote it wm xm. So now we have to decide what this m should be. Okay, I would love to show you a problem so that we'll see how once we change this m, how does it see, because I was making that picture if it's a linear line, if it's a parabola, if it's then what happens when we have third degree polynomial. I'll again go to the code window, I'll show you that, and after I'll take questions. Give me a second. What can I do is I'll fit a polynomial. So again I'll use my friends matplotlib and numpy. So here this is matplotlib and numpy. So I'll say definition fit a polynomial. Okay, definition fit polynomial. This is my x and this is my t and this is my degree. This is my input variable and this is my target and this is my degree. Okay, now I'll get this from in this numpy. I have a polyfit. I can just have this polynomial fit. I'll get them. So given this degree, I can have this polynomial. So what I'll do is I'll get the coefficients. I'll say coefficients is equal np polyfit, have this x, have this t and this degree. So it will give me the coefficient. It will give me these w's. It will give me directly these w's. Okay, this is basically the curve fitting. So this is that curve fitting. It will give me corresponding w0, w1, w2, something like that. Okay, and then I'll get corresponding values to this. I'll return this lambda function. Okay, this should work hopefully. So this is what I'm returning after that. So now let's call the I'll fit four types of degrees. I'll say when m is equal to 0, that is I have a line. Okay, and then I have this parabola, degree 3, degree 9 polynomial. So these are the things that I'll fit. Okay, and I'll also plot it. For let us generate some x continuous value, and give me a second. I'll just plot this with the same. I have to adjust this code. Wait. If you see this, what I have done is, so this is degree, these are my degrees, and then I have np linspace 0, 1, these are x continuous values, and then I am fitting this polynomial again, fit this polynomial. So this is my function, fit polynomial. Okay, and then I have this axis I, so I have to create this axis. So what I'll do is I'll create figure and axis. Give me a second. Okay, figure axis, these many plots, and I'll have this axis. Okay, now I am having a polynomial, fit polynomial, this x data and the t. Okay, this degree. So I am saying axis I give a scatter plot, and y fit is polynomial of this x continuous, because I am using the lambda function over here. So you can see if I plot it, let me just call this function, and I'll have a function make prediction. So plt dot type, and then I'll make predictions for these new values. Okay, let us draw this. Yes, you can see this. So when m was 0, you can clearly see a line. It just is passing through 2 points. Okay, nothing, man. There is a lot of error in here. And then when m was 1, so it became a line and a little bit sloped. And now after that, you can see when m was 3, when we had a third degree polynomial, okay, it gave a sign. When m was 9, you can see it gave error almost 0, but it is passing exactly through all the points. Okay, it is overfitting. So this over here is overfitting. Again, to reiterate this, so when m was equal to 0, so this is the thing that it found. Okay, and this is by np that polyfit. And when m was equal to 1, this is the line it found. Okay, and when m was equal to 3, because we're adjusting those parameters, we're adjusting that value of m. So what degree of polynomial do we want? When m was equal to 3, this is what it gave us, and then when m was equal to 9, and it actually gave the error of 0. But this is actually overfitting. So if you see on the on these predictions, you can see that this once we have the values which are we just have these input values, it will make a lot of mispredictions. Okay, this is the effect of m. Okay, so this we will see this model complexity again. So how many of you understood this? So once I was changing the value of this m, because I took how many degrees? I took degree 0, I took 1, 3 and 9. If I can check with 2 also, let's suppose I have degree 2 as well. Let's suppose this is 2 and this is 1. So here you can see this graph changes. So this is, let's suppose degree 1, 2 doesn't make much difference. You can see degree 3 and degree 9. Okay, if you keep on increasing, you are basically increasing the power of polynomial. You are initially with w0 plus w1 x. Okay, then you are with w0 plus w1 x and then plus, and then it was x square, and with the coefficients, its coefficients, and then this was a 9-degree polynomial. Okay, it completely fit it. And why? Because 9-degree polynomial had actually 10 parameters to learn, and these 10 parameters learned each data point. That's why it perfectly fitted it. Okay, and it passed through all of these points. If you can see it over here, okay, it passed through all these points. That's why it was able to actually pass through each and every point. But the problem over here is it is not a good prediction. The problem is that it overfit the data. It tried to memorize the data. So here if you see m is equal 3 was a bit better if you can see logically from here. Okay, m is equal 9 gave an error of 0, but it was on the cost of what its memorized data, because it tweaked and tuned the parameters, all these w, the parameters here were this w0, w1, w2 till let's suppose w9. So all these parameters were tweaked such that it passes through all these points, but we don't want that. We want generalization. This m is equal 3 was a better generalization than this m is equal 9. Yes, I think Arshan has a question. Can somebody read it for me? So what I have done over here is, if you see in the code, I have just used the numpy's polyfit. Okay, so this polyfit, because this error function, you have to minimize the error function, and this error function is in, let's suppose, the power of 2. Okay, it's a quadratic. If you see, it isn't quadratic. When you differentiate, it will become linear, and you can get a closed form equation out of that. Once you get closed form equation, you can get the direct values from these w's. Okay, you can get these direct values of w. That's what this np this polyfit does. So when you say this, I have to get coefficients. When you say np polyfit, so it does not do it automatically. It is basically done by NumPy. So NumPy is implement the algorithm by the help of which it tries to fit. It tries to find those coefficients, and these coefficients are w0, w1 till the degree of polynomial, whatever degree you have used. Okay, that's why I'm giving degree as well. Okay, once I have that, and after that I am trying to see, okay, if I increase the degree now. Okay, in this basically I'm giving only one coefficient. I'm giving two coefficients now. I'm giving three coefficients. Okay, even here I'm giving two coefficients. I'm giving three coefficients. So this is the one I am giving here. Let me just see if it's visible. So this over here. So here I have to learn w0. Okay, and then w1x. Okay, this is linear. So here I am learning three coefficients, w0, if I am correct. So here I am learning two coefficients. I am learning 3, and then going back here I am learning 4, and I am learning 10 coefficients. So this is this is, let's suppose, 3, because I am having 3-degree polynomial, so I have 4 coefficients to learn. So in the 9th degree polynomial, so I have 10 things to learn, so 10 coefficients to learn. So that's what this code is doing over here, if you see it here over here. So when I call this polyfit, it learns those coefficients. So in the first example, we just had 2 coefficients learned, w0 and w1. So once we increase the degree, so degree plus 1 number of coefficients are there to learn. So what I said is, the important point I made is over here. So when I add this 9th degree polynomial, so it gave it a 9 degree of freedom. Okay, but what happened is, it tweaked these w0 to w9 in such a way that it actually made them pass through all the points. This is bad actually. Why is it bad? Because I tried to memorize. This is called memorization, or this is what is overfitting in data, because I gave it so much degree of freedom. So that what happened basically is, it tried to tweak the parameters, tried to tweak this w0, w1 till w9 such that every point gets through that curve. Okay, but it is not generalization, because when you, let's suppose, give a point over here, so if you give a point that's actually on the sine curve, so this point, let's suppose, or the point which was following some, because sine curve will look something like this. Okay, something like this. So you can see all these points, it will fail to detect. But over here you see a much more sine like shape over here when m was equal to 3. But there's a contradiction. Okay, I'll leave you with a question. The question is more the parameters. So okay, overfitting is happening. So should I decrease parameters? Okay, should I decrease parameter? If I decrease the parameter, doesn't it mean that I am limiting the learning capability? Okay, if I decrease the parameter, does it mean I am limiting the capability? Okay, if I limit the capability, okay, what if I don't want to limit the capability, if I want to keep the parameters as high, so what should I do after that? Okay, so here I introduced many concepts. I introduced, okay, how can we think distribution up, because data can be thought of information, and information can be there can be a pattern and there can be a noise, and that's what I introduced. And then I said, okay, if we have to fit an algorithm, it can be a simple curve fitting algorithm, and then we should have a notion of how good is that algorithm, how good result are we getting. That's we introduced error functions there. And now I am leaving with your question. The question is, once I am increasing this number of parameters, because I am making the curve more complex, you can see that it is overfitting the data. Is it bad or good? So if introducing more parameters is making it overfit, is making the algorithm to overfit, is making the algorithm memorize data, so it is good to reduce the parameters. Or should I keep the parameters same, because if it gives me more learning capabilities, and what should I do then? Okay, can there be a solution? Okay, you should not search it on the web, otherwise you'll get it. I'll leave you with this question. I'll stop the recording over here. Hello and welcome. So we have been discussing about machine learning. Okay, so in machine learning, what we have done is, so we started with a synthetic example. So in that, what I said is, I said if you have to create a data, let's suppose in that we generate our own data by using a function sine 2 pi x. This is just the like high level summary what we have discussed in the previous lecture. Okay, and this lecture will follow the previous lecture. So in machine learning, we said okay, everything works on data. So now in order to understand the data, so what we assume is that this data actually comes from a distribution. So there is some generating function. There is some generating function. And this is the trend that we want to have. This is the trend, or this is the pattern I call. The trend, usually the pattern you have. And with this pattern, you have the noise in the real world. Okay, then what we did is we generate data by using sine 2 pi x, and then we added some noise with this. We also wrote the code for that. So we generated the data points. So in that we had this x, this was the input variable, and then we had a target variable t. This was the target variable. And then what we said is, we said once we have this, the goal is now, if you have this data input variable, so you train a machine learning model, you find an algorithm. So you will now have two types of sets of data. So first you'll be having a training set, then you'll be having a testing set, test set. Let's suppose we had 10 points over here, and we had, let's suppose 100 points, or maybe let's suppose 5 points. I'll keep it realistic. This training set, you will have to find an algorithm so that you show this data, the data that you have, or the data you generated. Okay, you want to learn this pattern, or you want to learn this generating function, the function or the distribution that this data came from. You want to learn that, and you have to train an algorithm based on that. But how that should be trained? So that when you test it on the test set, so somehow it should be generic enough to generalize on the test set. So when you are testing it on the inputs for which the target is not given, you should be able to come up with the target. Okay, that was the goal we had. Okay, to predict the t for the unseen data. So the goal you should keep in mind is to predict the target, that is t, target t for unseen data. And then I showed you the process how to generate this data, and we should not sort of overfit the data, and we saw a lot of these things. We saw visualizations, and then what we were doing is we actually resorted to the curve fitting. We said okay, if this is if we have the data, so we'll fit a curve on the data. We resorted to curve fitting. So if you remember this, okay, I'll just show you the code window so that you. So if you see it over here, this was the code that we wrote. So this was the data that we generated. So this is the generation of the data. I showed you how we generated the data, and after that we said okay, now we want to fit the curve. Okay, so after we are fitting the curve, I said what you can do is you have to choose this m. Okay, because you are having that curve fitting algorithm, and you have now different values of m. So if I write the equations, the equation that I think there was, let me just hide this again so as to show the equation. This curve fitting, so we shall, so there are two things now. There is this curve fitting, you have this y and you are given this x. Okay, and what you have to find w. So you have to find these w. So the equation basically you wanted is w naught plus, then you had w1 x plus w2 x square plus, and so on till wm xm. Okay, this is what we want to find. So I said this is sort of a linear combination. You can have a line, you can have a parabola, you can have degree order 3 equation, something like this, let's say, and you somehow have the combination of all of these in order to find the curve. So we are in a pursuit to find the sine 2 pi x. So this is the pursuit that we wanted to find. Okay, so this is what we did for that. So we said once you have to set this w now. So even you can use the 0 degree polynomial, 1 degree, 2 degree, 3 degree polynomial. So that's where this m came from. So this is called as model selection. So when you are selecting the model, so that's where we set this. So now you have the data. So you have degrees. You can start with degree 1, degree 2, degree 3, and degree 9. So in this, what you can see is this is degree 1. This is, let's suppose, degree 2, and then we have m is equal 3 and m is equal 9. So you saw this m is 3 is good. So this is underfitting. So we call this as overfitting. Okay, and then we asked a lot of questions about this curve fitting and stuff like that. So we'll take the things from here. Okay, so I just so I revised whole of this thing. Okay, now what we have is we have two functions. The first function was the function of curve fitting, by the help of which we are fitting the curve. So we have to adjust we have to find the w's, find these w's, okay, in this. So if you see the equation, so this is our equation. So in this, this x is the data point, this x is the input feature that we have, and we have to find these w's. Let's suppose if we use m is equal 3. So by this I mean I'll use a cubic polynomial. So what I'm doing is I'll say w0 plus w1x plus w2x square plus w3x cube. So this is what by the help of which I want to approximate sine of 2 pi x. So by using this, so here if you see, the x is unknown, so these things are known to us. Okay, so what we have to find? So we have to find w0, w1, w2 and w3. This is what we have to find. Okay, we can write them in a vector form, and w0, w1, w2 and w3. So this we named as w. Okay, so these were our parameters. So this is our function. So this was our curve fitting function. So we had two functions now. We have curve fitting function, and the second function that we discussed about is how good is this. So if you found these w's now, so you want to evaluate how good is that. So this was our curve fitting. So we are fitting a curve. So the problem is fit the curve so that it approximates this sine 2 pi x. So now in order to see how better is this, so we found an error function. Error function. If I make a small flow chart, okay, so how the problem goes. So you have a machine like this in which you feed the data. You have the data. Okay, this machine actually has knobs and dials. So it has this w0, w1, w2 and so on parameters till let's suppose wm. So these were the knobs. Okay, so from this actually this will give you a function or approximation function. Okay, you are just giving data, and based on this you are adjusting the knobs and dials so that you try to tune this whole function so that it represents your function that you have, the generating function. So now how good this is. So what you basically do is you give these w's, all these w's are given to another machine. Okay, another function. So function basically is like a machine. So this over here is called as error function. Okay, don't confuse between two functions. The first function is there which is actually fitting the curve to the data, and the second thing is saying how better is that curve. Okay, it's trying to find the error. So here error, it gives a number. Usually it gives a number. So this number tells you how better approximation this is. So that we checked with. So if when m was equal to, let's suppose 0, m was equal to 1, m was equal to let's say 2 or 3, m was equal to 9, we saw how better these things were. Now two functions again. One is our curve fitting function, and the second function is our error function. So error function tells you, it quantifies how good your approximation is, or how good these values of w's are. Okay, so we boiled down our problem to this. So we said y of x n comma w. Okay, so let's suppose this is our approximation given any input xn or xi, so whatever you call it. So this value minus then tn. So this is the actual target. So this was the actual target. So you want to see how far this was. So in order to make a diagram, let's suppose, because you want to approximate, let's say, this function. Okay, now you have this function, you come up with something function like this. Now if you see this, if you see a point on this and if you see a point on this, so this is how much it's off. This is the distance. Actual thing should have been this, but it's actually this. So here actual thing should have been this, but it is this, and actual thing in here should have been this, but it is this. So there is some discrepancy. Okay, there is some error associated with this. So that's why we want to quantify how much that error is. So what we said is, this is my prediction. Okay, and this is the actual value or the true value. So I'll just subtract them. I'll see how far they are. But you know that the distance can be negative, positive in this case, but I want to, because I am calculating error, so I want to make it positive. So what I'm doing is I'm squaring the term up. Okay, once I'm squaring this up, now I'm doing it for all the values. So for that I added the summation. Summation of n goes from 1 to n for all the data points. Okay, then I said I'll just add this 1 by 2 over here for the because this is a differentiable function and we have differentiated, and if you know the differentiation a bit, so that's why I want these 2's to cancel. Okay, this I called as squared error function. Based on this, I wanted to see, okay, given the values of particular w, I want to see how much error is there. So for that we chose different values of so we chose the different values of these m's. That's the code we have written in the previous session. So if you see this is m is equal to 1, this is m is equal to 2, m is equal to 3, m is equal to 9. Okay, this is where we were at. Now what I said is, I said this m is equal to 9 was overfitting, because it was going exactly through all the points, so it was actually capturing noise as well. So I said how to deal with this. So there was a contradiction question. So more the parameters, so it should learn actually more. And the other question, there were two paradoxes, okay, which at least when I was learning I could find these paradoxes. The first paradox was, because m is equal to 9, if you remember this, at m is equal to 9 we called it overfitting. Why? Because it was tuning to data too much, it was capturing noise as well, it was not generalizing. That's why we call it overfit. The first problem was it has more parameters, So doesn't it seem that if we reduce the parameter, we are reducing the model complexity? Okay, so if it has more parameters, does it mean we should have less parameters? Okay, this is the first question, a natural question that should occur to you people, that if it has more parameters, so it was overfitting. So does that mean I should come up with less parameters so that it does not overfit and it actually generalizes? This was the first question I asked. The second question was there, doesn't it seem counterintuitive that you have a function, you have a polynomial of degree 9, so don't you think that all the other degrees can be represented? Let's suppose if I have degree m is equal to 3, which we said it's the best fit, this was a good curve in that. So don't you think that this m is equal to 9 is somehow superset or somehow super encompassing this function also? So it looks counterintuitive, total counterintuitive, that having more parameters, why is it not performing good? Okay, that is the second question we have. Okay, let me do this. So what I said is, the second question we had is, so doesn't it seem counterintuitive? Intuition. Doesn't it seem counterintuitive, because this m is equal to 9 should somehow engulf m is equal to 3. So why is it doing so? Why is the better fit at m is equal to 3 and not m is equal to 9 also? Okay. So initially, as this higher poly, if you see, inherently include all these lower order polynomials. Okay, and theoretically it should at least perform good, at least perform as good as m is equal to 3. Okay, how many of you think that it seems counterintuitive? Because what I said is that this high degree polynomial m is equal to 9 is a high degree polynomial. Okay, it includes all the others are somehow the special cases of it. Okay, the lower degree polynomials. So theoretically, at least this should perform as good as m is equal to 3. Okay, and this data was generated using the function sine 2 pi x. One more thing is there. So we should expect that this predictor, at least the m is equal to 9 function, should approximate it better. So because if you know Taylor series, so when you expand these things into these powers, so the more terms you have, the better approximations you have. Okay, so we'll see this expansion also. I'm throwing too much maths at you right now, but I hope someday you will. So expansion. So what I'm saying is, the more degree polynomial you have, the better approximation you get. So we'll see that in Taylor series. Okay, so it again seems counterintuitive. So now we'll examine why is it so. Okay, I told you guys to sort of ponder over it, contemplate on these things. Okay, I hope you have done that. Okay, let me give you the answers why it happens. Why does it happen? So now we'll examine the values of these w's. We'll see. So once we have these different degree polynomials, what are the value of these w's? Okay, let me just write some simple lines of code. Now we'll not go to this error, we'll actually go to root mean square error. So root mean RMS value. So what is RMS? So again, you have predictor values y, x, comma w, okay, minus t of n, so this is xn, and you will square it. Okay, till here it was squared error. Okay, now for all the points, this is n is equal to 1 to n for all square. Now if I have to take mean, so I'll take mean by this, I just divide it by the number of samples or number of data points. If I have to take root mean square, I'll apply a root. Okay, again I'm telling you, mathematics is poetry, you should read it like poetry. Okay, so this y, x, n, comma w means prediction. You are giving the value xn, you have certain w's, and this is giving a value, and this is the predicted value. So when you are squaring it up, that means you are trying to find the distance, but it's a positive distance. Okay, this is squared error. Okay, now what you are doing is you are applying summation. This is doing for all the points. Okay, after that you want to find mean of that. So for that you are dividing by n, you are dividing by total number of points. Now in order to have this on the same scale, because it will square this up, okay, in order to have it on the same footage, on the same scale, so we are applying the square root so that the square gets cancelled. After we calculate this, so you are putting the under root so that if you are having a metric, if you have meter and you apply a square, you'll get meter square, something like this. So now in order to nullify that effect, you are putting this root over here. This is called as RMS, root mean square. So this is called as RMSE, root mean squared error. This is the first thing, this is squared error and it was mean. So this thing was squared error, and because of this is called as mean squared error, and because of whole of this root, it's called as root mean squared error. So squared error, this terms from summation to here, this is squared error. And once I apply this 1 by n, this is called as mean squared error. So once I apply this root, this is now root mean squared error. You can see mathematics is not difficult. The notations, if you get hang of notations, quite easy. Okay, and it's quite natural also. So now the fundamentals where we're doing this. Okay, now after we have this, so now what we want to do is, so we want to see the RMS value for different m's. For m is equal to 0, m is equal to 1, m is equal to 1, m is equal to 3, and m is equal to 9. I think that's what we were doing. So for all of this, we want to find RMSE. Okay, and corresponding to that, what we want to do is we want to find values of w. Okay, what are these coefficients? What are the values of these coefficients? Because we have to answer these questions. Because this seems quite counterintuitive. So I asked you these questions. The more parameters, does it mean we should have less parameters, and should we decrease the parameters? If not, so what should we do? So this question still stands. Okay, and here again the same thing. So all of this high degree polynomial should somehow inherently contain this lower degree polynomial. Then why is it not performing better? Okay, so we'll answer these questions. Let me write the code to do this, to find this RMSE and to find the coefficients. And then we'll see the training loss as well. And now what we'll do is we have to find this RMSE value and we'll try to find this error. I hope this screen is also visible. So again, I'll resort back to NumPy, Matplotlib and sklearn. So if you see this, I'm importing NumPy, importing Matplotlib as this PLT, and train test split, because I'll be having data set and I'll split that into train and test. Okay, then I'm also importing this mean squared error. I could have done it on my own. I would have just implemented the function, but it is already in sklearn, so you don't need to implement it. Okay, now what we have to do is we'll fit this polynomial. We have been doing this since previous class. So if you see this, so we are saying definition, fit this polynomial xt of this degree. Okay, and then what we are saying is we are trying to find the coefficients. So if you see this, okay, so this is the coefficients, NP polyfit, it will give me coefficients, and I'm returning these coefficients as well. So now I'll calculate RMS also. So, okay, so here I have a function to calculate RMS. It's quite easy, otherwise I would have. So if you see this definition, calculate RMSE, this is y true, y predicted. So it is taking this mean squared and applying square root. Okay, so I'm applying this mean squared error. So on that I have to apply square root. That will convert it into RMSE value. So I'm taking this y true value, y predicted value. So this y true basically is y x n comma w, that value, and this is y predicted value. This is predicted value. The true value is actually true value, and this is mean squared. And after that we apply square root on this. This will calculate the RMS. Now again I generate synthetic data. Okay, that we have been doing I think since class 1. So this is random seeds for the reproducibility, and then we have this 10 points. Okay, this is our main function sine 2 pi x, and this is some Gaussian noise with mean of 0 and standard deviation of 0.1. Okay, this is our target and this is our input. Now I'll split the data. I'll split it. Oops. So how to split? I'll use this train test split. So I can split it in any other fashion also, because I can use NumPy, I can use pandas and howsoever I want, but sklearn gives me this test train split, so I'm using it directly. So I'm having x train, x test, t train and t test. This is y actually. Okay, so I'm giving test train split. This is a function. So I'll give this x, t and test size. So test size basically is 0.3 and 0.7 will be, if this is 10 points. So 3 points among them will be test points and 7 points will be the training points, and random state is the seed. Now what I'll do is I'll make a list of these degrees, because I want to do it for degrees 0, 1, 3 and 9. Okay, that's what I want to do. And now I'll create the plots as well. Let me create how many plots? I'll create 2 by 2 plots. So if you see figure and axis, I'm creating plot of subplots 2, 2, figure size is this much. You should be well versed with this. So I'm putting this for plotting the curve. I'm also putting this continuous values of x continuous to generate smooth values for x for plotting continuous value. Now I'll store the train RMS, I'll store test RMS, and I'll also store the coefficient list. Okay, so what I'm doing is I'm having this train RMS errors. Okay, I'm also storing test RMS errors. Okay, this is for the train root mean square errors and test root mean square error and the coefficient list. These W's, W0, W1, W2, something like that. Now after that, what I'll do is I'll run a loop for all the degrees. I'll run a loop because I have to do it with degree 0, degree 1, degree 3, and degree 9. So I'll run a loop for this. This is for degree, for I degree, enumerate these degrees. Okay, then I'll fit this curve. Because I have written this, if you see, so here is my polynomial, fit polynomial. So this is what I'm calling over here. Fit polynomial with this x train and t train and give the degrees. So degree will be taken from this because I'm running a loop onto this, and then I'm getting a coefficient list which I'm appending to this coefficient. Okay, and then I am calculating the prediction for training and test to make the predictions. So I add a comment here, fit, I'll say fit the curve, fit the polynomial to the current degree. And then what I'm saying is calculate predictions for training and test set. So train prediction is polynomial. So whatever polynomial we got, give it to x train and it will make the train predictions. And now I'll calculate the RMS value. I have again written the function for RMS. So I'll just call that function. So here I have calculated the RMS value. So here it is, calculate RMS. So that's what I'm calling with this t train, t prediction, and it will give me the values. Now I have to append these values. So these values are to be kept in train and test list, this and this list. That's what I'll be doing. I'll be appending them to these two things. Okay, so I'm appending them to this, append this train RMS to this and append this to this. And once I have that, now I'll do the plotting. Okay, and this plotting should be quite easy to understand. Okay, so I'm doing the loop because I want all the plots. If you see this, I am plotting over here. This is a scatter plot for x train and t train, and then I'm saying this, we have this y fit, then I'm also fitting this and adding some horizontal line this and then these are just some titles and legends and stuff like that. Okay, then I'll at the end have this RMS comparison also. I'll add a plot at the end. This plotting code I'm not on purpose going through because you guys should be experts by now to read this because we have spent quite a lot of time to draw this plot. So this is the code. So now I'll run this code. If you see this, for m is equal to 0, okay, this is the line that we got. Okay, I'll resort back here. So if you see this, so these points were our training points, training data. So these blue points, this is our training data. So for m is equal to 0, this is a straight line, okay, that you can clearly see over here. So now this is our test data. Okay, and you saw clear there was an error. So that's why it's showing test RMS, train RMS is this, and testing RMS is this. Okay, and this is clear a line, and it is a misfit. It's not a good fit. It's actually a very bad fit. So now in order to go to here, this is equal to m is equal to 1. Again, the same thing. So this is training data and test data. We have only 3 points because we have generated 10 points, and among them we kept 0.3% of the data as training test data, 3 points, and 7 points as training. We could maybe increase points more in the next iteration. So if you see this is m is equal to 1. Again, you can see test RMS 3.14, a little bit less, and train RMS also a little bit less. Okay, now you saw that it is improving a bit. So you see that RMS, the error is getting lower and lower. Okay, so we expect it to monotonically increase. So now if you see the other graphs, so if you see RMS of 3 and this, so you see m is equal to 3. So here you saw train RMS 0.063, very good, and train test RMS 0.18, and it's very good. The error is very less, so that is evident from the graph as well. Okay, so this is actually what we call usually a best fit or a good fit. I should not call best fit, a good fit. This is a good fit. This is why I'm doing a curve fitting. So now if you see this, so I call this overfitting. So now it tuned to all the data points, it tuned to all these training data. Okay, this curve passed through all these blue points. It's covering through all the blue points. That's why you see this train RMS being 0.005, and you see test RMS is quite high. Okay, so this is what I call overfitting over here. Okay, now we were in this pursuit that we want to understand why is it happening. Okay, let me answer that question, why is it happening. So that answer is basically in the coefficients. So this is again training and test RMS difference because I just plotted the graph from this. And now if you see this, so see this details over here. This is degree 0, degree 1, degree 3, and degree 9. So what you can see is if you see coefficients, this is W0, this is W0 and W1. This is W0, W1, W2, W3, W0, W1, all the coefficients over here. So once you are increasing this polynomial, degree of polynomial, so you can see this coefficients, the value of coefficients is increasing heavily. So initially this was the coefficient value 0.125, then we have minus 1 point something like this. So after that it became 21, 32, 10. But if you see at degree 9, these values are quite high. These values are very high, except for a few. These values are quite high. So what this is telling you actually basically is, so it is tuning coefficient such that it is exactly capturing the points, and at the edges even, if I can go back here, if you can see over here, this is trying so hard to go through these points, and it has to make the coefficients value so high, okay, and then it's missing these terms actually. So this being the reason, so when you are having the value of coefficients very high, so it is trying very hard to go through the points, okay. Once that is done, so what will happen basically is, so when you have to go through this point, now it has tuned this W such that it passed through the point, it passed through that point. So giving very high weightage to W, so that you tune it to data, it creates a problem for us, okay. So I hope you understand the point now. The point basically is, it is giving coefficients such a higher value, so that if you see these edges, so if you see the edges over here, I'll call these things as edges, so it is trying so hard to go through them, so it has to make the value of W so high, so as to let this curve pass through the function, and that's what is creating actually the overfitting. Somehow if we could control these W's, okay, somehow if we do not let them explode either on the negative side or on the positive side, maybe we can cover this overfitting problem. The question now is, the first question was answered. So if you see the first question, the question that we had is this. So it has more parameters. Does it mean we should have less parameters? What I said if you somehow can manage with lower values of W, if you do not try so hard to give them so high values, so maybe you can even work with more parameters. You don't need to decrease parameters, okay. So why does it seem counterintuitive? Because it seems counterintuitive. Now the value of m's is getting changed drastically. If the m's were similar, it would have engulfed to all those things. It would have inherently shown the same pattern. But here, because it is trying so hard and the values are so extreme now, either it's very high or it's very low value. If I just remove the sign, you will see very high values of very high positive values and very high negative values. So now we have to resort to this. So even with the same parameters, what can we do? Can we do something so that it does not show this problem? Okay. So for that, what we have to do is, we'll have to do something. We'll have to add something. We'll have to penalize it. So do not increase W so much. So we'll ask it. We'll have to say it explicitly. Okay. I found the problem. The problem is that, again, I'll show you the problem. So the problem here, if you see, oops. The problem that we found is that once we look at these coefficients, initially they were good, they were in a good range, okay, the values were not quite high, but once you increase this W, it is overfitting because it's making these values quite high, and because of the high values, it is tuning to the noise also, it is capturing the noise. So now what I am trying to do is, I am telling them, okay, do not increase these values so much, because why? Otherwise you are learning the noise also. I don't want you to learn the noise. So how can I do that? Do not tune so much, okay, do not try so hard to go through the points, because if you try so hard to go through the points, you are increasing the values for these W's. Either it is hugely positive or hugely negative. Okay, it is evident from this. So now what I have to do is, I somehow have to penalize it. Okay, so this is the result. So what I am saying is, I have to penalize it. I'll take your questions maybe after I finish this. So how should I do the penalizations? Now I have to tell it mathematically. Okay, penalize it. This was my equation. Now you have to penalize. So what I'll do is, this was the equation. We had this. If we again come to, let's suppose, mean square, the squared error, summation of n is equal to 1 to n points, and we had prediction y of x n comma w, and then minus t of n whole square. Okay, so this was my thing. This was my error. So error of w. So I was getting error of 0. So but what it was doing is, it was changing these coefficients too much. It was giving them very higher values. So once you are giving them higher values, it is tuning to this noise. So what I actually wanted to, I want to penalize it. Okay, so once it gives more value to W, okay, somehow I should penalize. I should say, okay, so there should be a tug of war now. So tug of war in this, if it is increasing W, so I should do something to this so error increases. So I should do something so the error increases. So if it is increasing W's too much, if it is giving this W's too much attention, so what I should do is, I should somehow add something, somehow penalize it somehow, so that once these W's increase too much, so in the equation, I should add something which will bring it down. So I should add something. So if this W goes up, okay, if this W goes up, so what I should do is, I should keep on adding this error also. Okay, so the natural thing is, I'll take a norm of this W. I'll say W square. So what I'm doing is, because I found the problem. I found the problem was when we saw this when m is equal to 9. the coefficient value, these W's, they were getting very high values, and because of that it was tuning to the noise also. Now the answer to this was, I said if it is making these W's larger, so what I should do is I should penalize it, because the point was it was trying very hard to get this E of W is equal to 0. It was getting error is equal to 0 because of this. Okay, because of this equation it was trying to get error is equal to 0. But what I'm saying now is, because you are increasing W, that's how you can get this error is equal to 0. But if you increase W too much, I'll penalize you. So what I'll do is I'll add the square root. Not square root, sorry, I'll add the square of W. Okay, whatever W's you give me, let's suppose it gave 208. So I'm squaring that up, add, plus. So it is basically the dot product, W dot WT, W. Because we have vector W like this. This is W naught, W1, W2 and W3. Okay, so this is our W. So we are saying W transpose W. So this is a dot product of these two, and I'm this is the dot. This is called as norm 2. Okay, so this is what I'm penalizing with. So does it make sense? Because I told you the problem is happening because it is increasing W's too much, and it is getting this error function 0. Now I don't want you to increase W's. So still what I want you to do, I want to keep the W's in check. Once you increase the W's, now I have another term now. So this term will make sure that if it increases the W, this error will also get increases. So for how many of you made sense? So again, to reiterate here, this was the initial error function. So this error function, what it was trying to do is, if we were increasing the degree of the polynomial, as in m is equal to 9, it was trying so hard to get through all the points. As a consequence to that, it was increasing the value of these W's. Okay, that's the problem we figured out once we printed the values of these coefficients. So now what I have done is I have added this penalty term. So there's a tug of war going between these two things. So if this increases, okay, this will decrease. Okay, this somehow is inversely proportional. If you increase W's too much, you are getting the lower value of this, but you are getting higher value of this. If you decrease W's, okay, and if you take them nearly to zeros, so this will become 0, but this will be too high then. Okay, this value is too high. Now you have to find a balance. So this thing over here, if you see this W2, and then we'll say how much do you want to impact it. We won't just square it. We'll say let's have this lambda by 2 also here. Okay, lambda basically is, okay, I want to give this only this much weight. Okay, because this W square is too much, so I'll give this lambda some value from 0 to 1. Some value from here. Okay, if it is 0, so we are just removing this term. If it is, let's suppose 0.5, give half a weightage to this. So I am just adding lambda by 2, something like this. Okay, so now the equation becomes E of W. So error of W is equal. So I am taking the squared error. So this is y x n comma W. This is my prediction, and this is the truth value, the ground truth. Okay, and I am squaring this up, and after this I am taking it for all the points, and I am adding this 1 by 2 for later convenience in this numerical equation. Then in order to penalize it, I am penalizing it with W square. Now I don't want to give this equal to 1, so I am adding one more term, lambda. Okay, this lambda, what is basically how much weight should be given to this? I am just adding this lambda by 2. Okay, so this thing what I did so far is called as a regularization. Okay, so I have added this is called as L2 norm. Okay, norm 2. So this is what I have done so far. So if you see this now, it also depends on lambda. There are two things now. The first thing was m, and then we had lambda. Okay, you are minimizing this equation. You have to minimize the errors, but you have to minimize with respect to W's only. Okay, you cannot minimize with respect to lambda and this m. Okay, this lambda and m, they have to be fixed. They have to be keep fixed. You should fix them. Fix before training. You should fix them before training. So once you fix them and then you minimize this, okay, because you keep in this W and you want to find this W star. W star is the values for W for which this equation becomes minimum. This equation gives us a minimum value. Okay, and these things lambda and this m are called as hyperparameters. Okay, so this is the function. Okay, so this technique is also, so this regularization actually sometimes, because we can solve this equation in closed form. So here usually in machine learning deep learning we add the regularization, but we have closed form methods in statistics. We have a special method which is called a shrinkage. We can shrink it, okay, which reduces the magnitude of these coefficients and that suppresses overfitting. Okay, but in neural network this is common to because there are all these weights are there. These W's are weights. Okay, this is called as weight decay. Because you don't want weight to take very high values. Okay, that's why you want to do this regularly. You don't want to take this weight decay. So if let's suppose you take this lambda is equal to 0, if you take lambda is equal to 0, this whole term will vanish. Okay, and this will become a normal loss function or a normal error function, sorry. Okay, and you have to balance between this lambda. You have to choose this lambda very wisely. And how to do that? You have to maybe do some searching, or you have to do a hit and trial so that to find this lambda and m, why does it perform good. So that's why in order to find this m and in order to find the good values for m and lambda, we do what's called as cross validation. We'll see the details of all of these things, but I just wanted to show you what is this cross validation for. So what basically we do is, so we have these hyperparameters. Okay, so we try to minimize this error function. So we can't do it with jointly with w and lambda. Why? Because w will always go to 0. So it'll, so let's suppose this is the error function. So the error function that we had, I'll just copy this error function. So this is the error function that we have. So if I jointly want to decrease, if I jointly want to minimize this, see the scenario over here. So the natural question for the mathematicians is, why don't you jointly use this lambda also, with respect to lambda also use this while you are minimizing the problem is, this will again put lambda is equal to 0, because the whole goal of this is to make this error value as 0. So it will make this error value as 0, it will give very high values to w, and it will make this lambda as 0. Okay, so this will again overfit. Okay, so similarly when you have this m, okay, so it will tend to overfit the model. So if you minimize this, the error function that we wrote, if we minimize this with respect to w and lambda jointly with this, so we have now joint minimization with lambda, m and w's. So what it will do is, it will put lambda is equal to 0, again it will do overfitting, it will give very high values to this w's once you do it with m. So you have to fix these two things. That's why they are called as hyperparameters. You have to fix this before training. How many of you are able to see the problem there? If I jointly do the minimization with lambda and m, so the problem will, it will take lambda to 0. That is not the thing we added lambda for. So if you give it w, if you give it m, okay, learn m also from the data. So it will try to learn m as high as possible, and it will give w's as high value as possible, and it will try to overfit, because the whole goal of this equation is to make the error 0. So if it has access to this lambda as well as to this m, so it will try to overfit. So it is better to have the control with the user. Okay, you have this, you just learn these w's. Okay, that's why we call these hyperparameters. Okay, so this optimization. So for this, what I said is, in order to optimize values of lambda and this m or hyperparameters. So what we do is, so we do validation. Okay, so what we basically do is, I'll just briefly cover it because we'll have detailed lectures coming on this. So we have the whole data with us. This is our whole data. So we are keeping this train data with us. Then we had this test data. So what we basically do is, we'll have a validation also. Then we'll have test. So this thing is what will be used, and this thing is totally unknown to the model, So on this you will train. Okay, because you are fixing the hyperparameter. You will give some m is equal, let's suppose m is equal to 2 and lambda is equal to 0.2, something like this. If you gave this, and now you have to test it, you will not use it on test set, you will use the validation set, and you will see how better it performs on validation. So after that, what I do is, if you saw it is giving a lot of, it is going train error was, let's suppose, good, but validation accuracy, validation error is not good. So you will change this. You will say m is equal to 3, lambda is equal to 0.5. Okay, again train it, again test it on validation set. So once you are convinced, okay, now the train error or the train loss is good and the validation loss is good, and at the last you are giving this test error. Okay, so from this validation set, you are tuning these parameters. Component cost is increasing, so there are a lot of types of this cross validation. Okay, so there can be S or K fold or S fold, they call it S fold or K fold cross validation. Okay, this is one of the techniques. Then there is leave one out cross validation, LOC, leave one out. So these are all the methods of cross validation. We'll see all of these. But the drawbacks are, so you are increasing computation cost and then tuning multiple parameters. It can be prohibitive as the number of combinations go exponentially. Let's suppose if you have 10 parameters to tune. Okay, so then you see this is a combinatorial problem, so it will grow exponentially. Okay, again there will be a lot of resources to use. Okay, so you'll have to settle down on the hyperparameter. The less the hyperparameters, the easier it becomes, because maybe sometimes you, and that's why again a primer over here or disclaimer. So when you are reading any papers, usually what I have seen, good papers, they give hyperparameters as well, but the papers who don't give hyperparameters, so it's very hard to reproduce them. Why? Because they are not giving hyperparameters, and they found certain of these results or all of these results on certain hyperparameters. There are particular values for hyperparameters. So it is very hard to replicate them. You are getting very bad results because you don't have parameters. Let's suppose there are maybe, let's suppose 2 to 10 have parameters. So if you don't know value to these, so it is very hard to reproduce these papers. Okay, this is just a primer because sometimes you will be banging your head on the wall if you are reproducing a paper and you are not getting exact results. So you must look, have they given the value to have parameters. Okay, so now I'll show you how this lambda has an effect. Now we'll do the same with this, same with m is equal to 9, but now we'll use this regularization term. Okay, that's what I'll show you now. Okay, let me just copy the whole code so that I don't have to write all of this one by one. So I hope that you will understand it. After that, you'll pause the video and you will read the code on your own. Now what you see is here fit polynomial but with regularization. So now I am adding this. Okay, you don't have to understand this right now, but probably once we go to linear algebra, we'll understand this, and then I'm evaluating this thing. But the degree over here is 9. If you can see clearly, degree is 9. Now I'm adding these terms also, this regularization term. So now if you see this, so this is lambda is equal to minus 18. Okay, so lambda has a huge effect. So at lambda is equal to minus 18, so you have this value. So the function is like this. Okay, you saw still it approximated it very nicely. And in here, if you see lambda is equal to 0, by lambda is equal to 0 basically no regularization used. So there was no regularization used. So you see this curve is not good again. Okay, so this is very bad fitting. Okay, but in here if you see, so this is actually true function, this is fitted function at lambda is equal to 0. So this is data and true function and the fitted curve. So you saw that regularization has an effect. You saw this actually tried to approximate it quite nicely. Okay, and if I want to show you one more function, that is maybe the training loss and the test loss, let me show you that also. So this you can see it. Now there is no problem with this. So this is the test error, training error. So initially what we had is the training error was decreasing, but the test error was very high. Okay, now you can see this. So that problem also got somehow solved. So here we have high train error again now, and the test error is obviously same. So initially what we had is this test error was almost hitting 0 when this w was equal to 9 and then m was equal to 9, and the training error was hitting 0, but the test error was going very high. But here if you see, when you added this optimal regularization, so what happened is now the train error is also going high. Okay, so that you can clearly see. And even with this adjusting lambda, so lambda is equal to 0 basically means no regularization, m is equal to 9. Okay, and this is lambda starting value from minus 16 to this. So you can see that optimum values you get around here. Okay, so I hope I covered some of the basic concepts of ML and deep learning. So we'll see these concepts getting repeated everywhere. Okay, so most of these concepts we'll take one by one and thoroughly dissect them, but this example was there to showcase a lot of things, showcase how data is generated and what the physical phenomenon that might generate, and there is a function beneath that, and we have to approximate the function, and there is noise, we should not overfit, we should not underfit, and there are a lot of parameters to be tuned, and a lot of terminology introduced. So I hope that you understood this example. So I'm stopping the recording over here. If you have any questions, I'll take them.